Alright guys, I have a quick question here from section 3.5. This is number 10. This is a classic example of when you want to use logarithmic differentiation. So notice that this is in section 3.5. Section 3.5 is about implicit differentiation to start with, but part of implicit differentiation is logarithmic differentiation. Now, logarithmic differentiation is when you introduce logarithms into an explicitly defined equation, but the reason you do that is because the logarithms will help you to differentiate. Okay, they'll make the derivative easier to come by. Okay, so we're going to use logarithmic differentiation here, even though there's no logs here to start with. We're going to essentially take the log of both sides, do some algebraic maneuvering, and this will allow us to take the derivative easier than it is right now. Now I'll show you another way to do this. I'll show you just the direct way without logarithm differentiation, but let's do logarithmic differentiation first. So with logarithmic differentiation, we take the log of both sides. So we'll take I say log. Natural log is easier because those derivatives were easier. You could take just log base 10, log base anything, but natural log is going to be easiest. So let's just take the natural log of both sides. So you have to take the natural log of the entire left-hand side and the natural log of the entire right-hand side. That, in general, that's just a technique you can use if it ever helps you to solve an equation. Just like you can add the same number to both sides, or multiply by a non-zero number, or divide by a non-zero number, you can take the log of both sides. So here we're going to take the natural log of the left-hand side. That gives us natural log of y equals the natural log of x to the x minus 8 power. Okay? Now the left-hand side, let's just leave that alone for the time being. Natural log of y equals, but what does the law of logarithms tell us here? The law of logs, or one of the law of logarithms, says we can take the exponent from inside the argument and multiply by it in front of the log. So we could say this: x minus 8 times natural log of x. We could rewrite the right-hand side just like so. Now, what's nice about that is that now we can take the derivative pretty easily of this right-hand side. That's not bad to do at all. Okay, now you could distribute if you wanted to. It's not necessary. What I would do is just leave it how it is and take the derivative using the product rule. Okay, like here's one function is x minus 8. The other function is natural log x, and use the product rule. Left-hand side is also easy to take the derivative of. So we're going to use implicit differentiation now. Even though our original function was explicitly defined, we're going to rearrange via logs and use implicit differentiation. So what's the derivative of well, let's just go ahead and say the derivative of natural log y equals the derivative of x minus 8 times the natural log of x. Now what's the derivative of natural log y? Well, that's just 1 over y. But since we're taking the derivative with respect to x, we have to multiply by dy dx. Okay? Now, this is a product like we just talked about, so that's the derivative of the first function, x minus 8, times the second function, natural log, plus the derivative of the second function, natural log x, times the first function, x minus 8. Okay, so there is the derivative of the entire left-hand side. Now let's see what happens here. So we still have a 1 over y dy dx equals. Now what's the derivative of x minus 8? The derivative of x minus 8 is just 1. The derivative of x is 1. The derivative of negative 8 is 0. So that's 1 times natural log of x, otherwise known as just natural log x. Now what's the derivative of natural log x? Okay, that should be an easy one that we all know now. It's just 1 over x. So this is plus 1 over x times x minus 8. So that's x minus 8 over x. Okay? Now, I want to solve this for dy dx, of course, which means I need to multiply both sides by y. But before I do that, I probably wanted to combine this left-hand side. Add, get a common denominator and add. So what I can do here is the common denominator is going to be x. Let's just multiply by x there and x there. And now I have a common denominator, and I can say that 1 over y dy dx equals x natural log of x plus x minus 8 over x. And now we see, just to solve for dy dx, I multiply both sides by y. And so I can say that dy dx equals y times x natural log x plus x minus 8 all over x. Now here's the thing. We weren't forced to use implicit differentiation here because our original function was explicitly defined. We know what y equals. Now the reason I'm saying this is because we can actually substitute down here that we know that y equals x to the x minus 8 power. Okay? There's no reason to leave a y there because we know what y equals, because this function was explicitly defined to start with. So we can say this equals x to the x minus 8 power times x natural log x plus x minus 8 all over x. Now the last little thing to do is to notice we have an x raised to a power on the numerator and x raised to the first power on the denominator. So we can use our rules of exponents, namely the rule that says, let's see here, the rule that says x to the a over x to the b can be reduced to x to the a minus b power. So going back here, we can say that this is x to the x minus 8 power minus 1. We could say this is x to the x minus 8 minus 1 power, otherwise known as x to the x minus 9 power times x natural log of x plus x minus 8. And there we are. There is our final derivative. Now, I mentioned earlier that there's another way to do this. Okay, here's the other way to do this. Let's see, let's change colors. Okay, we could say that this right here is equal to, let's see, e, actually I need to give myself some more room. Let's go down this way. We could say that this is equal to e to the natural log of x to the x minus 8 power. This is another technique that's pretty common in solving equations. You can take both sides of your equation and essentially, well, here's what's going on. We have e to the natural log. Those are inverse functions. So since they're inverse functions, they undo each other. And so this right here is exactly equal to x to the x minus 8 power. Okay, so one of these techniques that is a consequence of the law of logarithms and exponents, but it works out nicely for us. Now, why is that true? Because we can rewrite that again as, let's see, e to the x minus 8 times natural log x, right? That's just bringing the exponent out in front of the log, just like I did right here in this second step over here. Okay, now why did I even do this? Because I know how to take the derivative of e raised to a function. Okay, this right here is in the form e raised to the u power, and I know how to take derivatives of that form. Now, how do we take the derivative? We could say in this case that y prime equals, okay, e to the u is the derivative of e to the u is just e to the u, so e to the x minus 8 times natural log of x power times the derivative of that exponent, x minus 8 times natural log of x. Now, have we already done this? We just did it right here. The derivative of x minus 8 times natural log of x, well, we already know that equals, so let's say we have e. Actually, let's go ahead and rewrite this. What do we know that this equals right here? This right here, we said was our starting point, was this right here. Those two underlying portions are exactly the same. They're just rewritten using a technique from algebra. So what I can do is just say, okay, that portion right there is equal to this, so it's x to the x minus 8 power. Now what's this? That derivative right here is the exact same thing I found right here. So it's this right here. Actually, I combined the. So I already combined it. So let's go down here. So it's here. Oh, here. But then here's the expanded version, and then here is another simplified version, and here's like the final version right here. Okay, that's when I simplified the fractions here. Okay, I added the fractions. So I could say replace with this right here, which is, oh, wrong color there, which is, we found was, wrong color again, we found that that was x natural log of x plus x minus 8 all over x. And what do you see here? This step right here is exactly the same as this step right here. And if we simplify one more time, just like we did previously, we get, using this rule right here, rules of exponents, we get x to the x minus x to the x minus 9 power times x natural log of x plus x minus 8. And here we see that we got the exact same solution in both instances. Now, this one looks a lot shorter, but it's because I skipped these steps because I already knew what the derivative right here was. I already knew what that highlighted yellow derivative was. So don't think that this way is super easy. I just was able to already know what this derivative was here because I found it just 5 minutes ago. So they would be about the same length either way. If you remember this little tool from algebra, feel free to use it whenever it's applicable. It helps you a lot of times when you have a variable base raised to a variable power. We did an example the other day. It was like x raised to the natural log of x. So a variable base to a variable power. If you have, like, say, x raised to the 5x power, again, variable base to a variable power, this technique, either of these techniques, will really help you out. So if you have any more questions, feel free to ask. I hope it's been helpful. See you soon.